All right. Should be everything. All right. Good evening. Hello. So today we're going to be going over the 2015 exam 2 review. So yeah, let's get started, I guess. So you'll notice in this exam we have two new sections. Is it two or three? Three new sections. So the first new section we have is reactions, which is you're going to be working through like reactions that Dr. Bean is going to be testing you on. So this is going to be, and this exam is going to vary from SN2, SN1, and E1 and E2. So it's not going to be too bad. And then the mechanism, most of the time it's going to be an SN1 and E1 reaction. And this, yeah, so this one we have an SN1. And then a synthesis problem, which is going to take a little bit of thinking, but I'm pretty sure you guys will be able to get through it. So we'll start again with the nomenclature. This is going to be on every exam, so it's good to know. So on the QR code that you guys got, number 3 asks you to provide a Fisher projection, but I've changed the question number 3, so that's because the Fisher projection will not be on your exam. So that's why I've changed question number 3. So yeah. Anyway, I'll start with number 1. So the first thing I want to do on this is I want to number my parent chain. So in this one, I know my parent chain is going to be the cyclopentane, right? But I don't know how it's going to be counted. So there are two ways that we can count this. We can count this 1, 2, and 3, and also the other way around. I'll add the forms 5, and then the other way around, which is going to be 1, 2, 3, 4, and 5. Notice how I started the numbering where there's going to be substituents. So we know that substituents are going to be like we're going to have substituents on carbon 1 since it's going to be a cyclo. So we started at each part of the substituents, and now we're going to see which ones are going to be prioritized. So which numbering is going to prioritize. So on carbon, with the red numbering, we have substituents on carbon 1, carbon 1, carbon 3, and carbon 3. And it's the same with the blue substituents, right? 1, 1, 3, 3. So now we're going to go to naming. So since they both have the same numbering, we're going to go to the name of the substituents. So from the blue numbering, we have on carbon 1, we have a cyclopropyl. So we'll just write like subs right here, and we'll just label them out. So cyclopropyl. And then we have 3 methyl groups on carbon 3. Or we'll have 3 methyl groups on both, so we'll call that just trimethyl. So we know that we're going to have carbon 1 is going to have the one. So carbon 1, so between the two numberings, red and blue, carbon 1 is going to be the one with the substituent that comes in the substituent that comes first in the alphabet. So in this case, it's between cyclopropyl and methyl. So we're not going to include the tri in there, just the methyl. So we know that C comes before M. So the numbering that puts the cyclopropyl group on carbon 1 is going to be our main, is going to be our number 1 carbon. So that's going to be our blue numbering. So our red numbering is going to be incorrect. So we're going to keep the blue numbering. So we know that our cyclopropyl is on carbon 1. So 1-cyclopropyl. And then we have trimethyl on carbon 1s, 2, 1, 3, and 3. So what we're going to write for the trimethyl is 1, 3, 3. And then our parent is the cyclopentane. So we have almost everything. One last thing we need to check is stereochemistry, right? So on this exam, you're going to have 2 types of stereochemistry. You're going to have alkane stereochemistry and RNS stereochemistry. So alkane stereochemistry is going to be E and Z. And so I'll write that down actually. Alkene is E/Z. And just chiral carbons, is going to be R and S. Okay. So the difference between E and Z is that the biggest groups on the alkenes are going to be on the same side or opposite side. So if we have an alkene that looks like this, so notice how on each of the carbons we have the biggest group on this first carbon. We named them 1 and 2. The biggest group on this first carbon is an ethyl, and the biggest group on the second carbon between that and the hydrogen is this methyl, right? Since they're on the same side, we're going to be calling that a Z. So Z for same side, so same side, and then E if they're on different opposite sides. So if that, say that ethyl was, instead of being up there, it was down here, right? If it was down here, then it would be E, so opposite. And then R and S, I guess I'll just go over on this question. So RNS, we're gonna start by carbon 1. So on RNS, we have to first identify a chiral carbon. So a chiral carbon is going to be a carbon that has 4 different groups on it, right? So carbon 1 has 4 different groups on it, like that. Carbon 2 does not because it has 2 hydrogens, right? Some might say like carbon 3 is, but notice that it has 2 of the same methyl groups on it, right? So that means this carbon is not chiral. So even though it has 4 groups on it, 2 of the groups are the same, so it doesn't have any chirality, right? And then 4 and 5 are the same as carbon 2, so they're not chiral. So the only chiral carbon we have is carbon 1. So we can look at this. So carbon 1, now we're going to identify the largest group that's connected to the carbon, right? So this carbon has 4 attachments, right? Has an attachment there, to this methyl group, and to this next carbon over, right? So between them, we have 1 carbon with 2 hydrogen bonds and a carbon bond. So a bond to a carbon, so CHH, right? This carbon, which has 2 bonds to carbons and 1 to a hydrogen. So it has 1 hydrogen, 2 carbons, so CCH. This one has 3 hydrogen bonds, so not C, just HHH. So notice we're not looking back from this. So if we're gonna look at like this top carbon where this red is, we're not going this way, right? We're just looking ahead. So ahead is only going to be attached to 1 carbon and 2 hydrogens, right? It's not going to be 2 carbons because of the back. So now the last group we have is attached to 2 hydrogens and another carbon as well. So this is attached to C, H, H. So between these, the biggest group is going to be our cyclopropyl group, which has 2 bonds to carbons and 1 to hydrogen. So this is going to be number 1. We'll just label that number 1. Now, we have 2 of them that are pretty much equal, and then the third one, the CH3, which is are going to be our smallest group, right? Because while the other ones have bonds with carbons, the CH3 only has 3 bonds with hydrogen. So now we have to decide which one is going to be bigger between the CHHs, right? So what we have to do then is we have to go to the next carbon over. So if we go from the top way, so the top carbon, from carbon 5 to carbon 4, we have C bonded right here, or not there, but we have C bonded right here like this. So this carbon right here. Oh, what am I doing? Okay, so this carbon right here, we have 2 bonds to a hydrogen, so H and H, and then we have 1 bond to the carbon that's down here, so C. So this one's another CHH, right? But if we go across from the bottom side from 2 to 3, we're looking at this carbon, and this carbon is attached to 2 different carbons. Actually, three different carbons. So it goes up, to the right, and to the left, or wedge and dash, right? So it's CCC. So between these two, CCC is bigger than CHH, right? So this one is going to be the bottom group is going to be our number 2 group, and then the top number 3. So now what we want to do we want to draw an arrow from 1 to 2 to 3, right? So we're going to draw it this way, right? And this arrow is clockwise. So whenever we have a clockwise arrow, we have an R, stereochemistry. And when we have counterclockwise, we have S, right? Whenever our biggest group is going to be on a dash, though, we're going to flip it. So because our biggest group is on a wedge, we're going to keep this. So right now we have R, and we're going to keep it as R. So our stereochemistry is going to be R. So now that we have everything, we can name this. So this is going to be an R dash 1 cyclopropyl dash 1 comma 3 comma 3 trimethyl cyclopentane. Any questions on that? Yeah. So when you're finding out stereochemistry, you're gonna look at the one with the biggest group first, right? So we're gonna number them from biggest group to smallest group, right? So in this case, our biggest group was the cyclopropyl group, right? You saw how it connected to 2 different carbons, where the other ones only connected to 1, right? So between those two, we have a tie, and then we keep going down the chain until we have a tiebreaker. And from that tiebreaker, that's when we we break the tie. You know what I mean? That makes sense? Any other questions? No? Okay. So number two, we have an alkene structure. So this is going to be a different way of naming. So whenever we have an alkene, we want to get the most amount of double bonds in the longest chain possible with the most substituents, right? So we can number it this way: 1, 2, 3, 4, 5, right? But notice how this one only, although it has 2 double bonds, it only has 1 substituent, right? So whenever that's not going to be our chain, because we can have a chain with more substituents, right? So our chain with the most substituents is going to be 1, 2, 3, 4, and 5. So in this case, we have 2 double bonds in it, which is the most we can have in any given chain, right? It's the longest chain with 2 double bonds that we can have, and it has the most amount of substituents, which is 1, 2, and 3. But we don't know if it's numbered properly. So important that we do it backwards and forwards. So we'll go backwards as well. So 1, 2, 3, 4, 5. And remember, first we're gonna look at where the alkenes are. So we're gonna look at this like which double bond the alkenes are at, right? So with the red numbering, our alkenes are at carbons 1 and carbon 4, right? That's fine. But then with the green numbering, our alkenes are also at carbon 1 and carbon 4, right? So because we have a tie in that, we go to the next one, which is going to be substituents. So now we have to determine which carbon each substituent is on, right? So this is the alkene bonds. And now we can look at the subs. So which number carbon the subs are on. So we have a substituent on for the green numbering, we have a substituent on carbon 1, carbon 2, and carbon 3, versus on the red numbering, we have substituents on carbon 3, 4, and 5, right? So we want our subs to be at the lowest number, so we're not going to take the red numbering. We're going to take the green numbering instead. So we're going to use the green to name this equation. So now we can name our subs. So 1 dash, I don't think you guys have learned that it's a benzyl yet, so, oh, not benzyl. It would still be a cyclohexyl, sorry. 1 dash cyclohexyl. So we have a 1 cyclohexyl, 2 dash bromo, and then 3, so we have this substituent on carbon 3, right? This is an ethyl like it has 2 carbons. So 1, 2 carbons, so ethyl, right? But since it has an alkene in it, we're gonna call it ethene, like ethene, and then YL. We're gonna add the YL at the end. So this is gonna be a 3-ethenol. So one important thing to note is that whenever you have an alkene as a substituent, often you're gonna have to put the number carbon that the double bond is at. But for this one, because it's just an ethenol, there's only one position it can be at, so you don't have to worry about it. But if it was maybe like a propanol, like it had something like this, then you would call that a 3-1 3-1 propanol. That makes sense, so that you can show that it's on carbon 1 instead of carbon 2 and 1 and 2 instead of 2 and 3. So that's going to be one thing to take note of whenever we have this. In this case, we don't have to worry about it. So we're just going to call it 3-ethenol. And now we can have our parent chain named. So our parent is going to be a pentane. So we have our 5-carbon chain, pentane. But remember, since we have the we have the alkene, the double bonds in it, we're going to go from pentane to pentene, right? But since we have 2, we're going to go pentadiene. So instead of just saying ene, we're going to start with 2. So penta and then diene. So it's the same as the pentene, right? It's just that we're showing that it has 2 double bonds in it. That's why the di is there. So this di tells us that there's 2. So there's di, tri, tetra. That's pretty much all you have to know. So di, tri, tetra, tri is 3, tetra 4. So yeah, and then now what we can do is look at stereochemistry. So now we have alkene stereochemistry, no more RNS. This time we have E and Z, right? So between this, we have 3 double bonds here, right? So 2 of the double bonds that we have, they have 2 of the same groups on one side, right? So this has 2 hydrogens, this has 2 hydrogens, right? So in this case, we can't really do anything in terms of stereochemistry, because we need 2 different groups on each side. But for the double bond on carbon 1, we have 1 group, 2 groups, 3 groups, 4 different groups, right? So we're able to do some stereochemistry with this carbon, or with this double bond. So if we're going to do this, what we have to do is first identify which one is the biggest group, right? So we're gonna do we're gonna determine that by looking at the first one between the the first thing the double bond is bonded to between them, right? So on the left, on this double bond 2, on carbon 2, the double bond is connected to bromine and a carbon, right? So between these 2, the bromine is bigger, right? So we'll call this just 1. And then now we have a hydrogen versus a cyclohexyl group, right? So between these 2, we know that the cyclohexyl group is bigger, so this is going to be 1, right? So our biggest groups are on opposite sides. So whenever they're on the same side, it is Z, right? So if they're on opposite, it's going to be E. How to write A? Let me change that. So E, right? So in this case, our stereochemistry is going to be E. So whenever we're starting, we can just start the name, E dash, and now we have to make sure that we put these substituents in alphabetical order. So we're going to start with the bromo, then the cyclo, then the ethenol, right? So 2 bromo dash 1 dash cyclohexyl dash 3 ethenol. and then our parent finally. So we have to make sure that we put the number of the double bonds into the parent name, right? So we have 1, 4. I should have put that before, sorry. 1, comma 4 right here, like this. So it's going to be 1, 4 dash 4 pentadiene. Or we can do instead, we can just write ethynyl like the like as in ethynyl penta dash 1 comma 4 dash diene. So both of these answers would be correct. Are there any questions on that? Yes. So on this carbon, on carbon 3, we have a substituent, right? This substituent is an alkene substituent with 2 carbons, right? So we have ethane, right? Ethane is a 2 carbon substituent. And then because it's a double bond, it becomes an alkene. So this becomes ethene, right? And to indicate that it's a substituent, we're going to add the YL ending. So ethene L, right? Yeah. Does that make sense? Anyone else? No more questions? Okay. Yeah. So E is whenever the biggest group on double bonds. So if there's R prime, R double prime, R prime prime prime, right? So between these three groups, if R and R prime are the biggest, then it's Z, then Z. But if R and R prime prime are biggest, then E, right? So it depends on the conformation. So if R and R prime are the biggest, they're on the same side, the biggest groups. So it's going to be Z, right? But if R and R double prime are the biggest, they're on opposite sides of each other, it's going to be E conformation. It's going to be like in terms of the groups on the periodic table. So the lower it's going to be, the lower group it is, the bigger the molecule it's going to be. So like carbon and bromine. So carbon is if you see on that right there, carbon is on the second group on the periodic table, right? But bromine is on the fourth, right? So same difference. Just in that way. Will be bigger, yeah, because it's a bigger group. Yeah, as it goes down, it gets bigger. Um, yeah, you can use atomic number. That's fine too. Any other questions? No. Okay. So this one, this is a question I added in. The other question that's on your exam is like draw the Fisher projection. So I don't think you guys are gonna have to do that on your exam, so don't worry about that. So in this one, we have an alkene, another alkene naming, but this time we have it in a slightly different form, right? So what we can do here is we can start with honestly I don't like this kind of drawing, so I like to draw it out myself after this, right? So we have the CH2 CH, right? C, which is bonded to our H's, bonded to a C, bonded to an H, bonded to this carbon is on a wedge, right? C, which has an H attached to this way. The C with CH3s, CH3, CH3, and then we have dash down here, CH2, 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 CH3. So in this one, we have a pretty easy way to number this, right? We're going to start with the alkene because we want the alkene to have the lowest number on it. So we'll start 1, 2, 3, and then now we come to like a cross, right? So we can either go right onto the wedge, and that causes it to be 1, 2, 3, 4, 5, or we can go down onto the dash, which is going to be 1, 2, 3, 4, 5, 6, 7, right? So we're going to go with the one that takes us all the way to 7. 4, 5, 6, 7, right? So this is going to be our parent chain, right? So we have a heptene parent chain. So parent is going to be 1 dash heptene. And now we can label the groups that are on it. So in this one, we only have one substituent, which is going to be this T-butyl group. This CCH3 is going to be T-butyl. So we're just call that T-butyl, tert-butyl. So this is going to be on carbon 3. So sub on carbon 3, tert dash butyl. Right? And that's all that we have. Now we have to look at stereochemistry, right? So between this, we have a double bond and we have wedges and dashes, right? So our double bond, notice how we have the same group, the CH on the same carbons, right? So this carbon has 2 hydrogen groups, which are both the same. So in this case, we're not going to have any E or Z. So no E and Z. And now we can do wedges and dashes. So we're going to look at the biggest group, right? So our biggest group in this one, we look at this middle carbon right here. So I'll circle it in purple. So we're going to look at this carbon, right? Because this is the carbon that has the wedges and dashes on it. So between it, we have one carbon on the wedge to the left that has 2 bonds to carbon and 1 bond to hydrogen. We have this hydrogen up top, so just hydrogen. Then we have this carbon, which is bonded to carbon 3 times. So it has 3 carbon bonds like this. And then we have this carbon at the bottom, which has 1 bond to carbon. So it has 2 bonds to hydrogen and 1 to carbon. So CH. So now we have a clear way of telling which one is the biggest group, small and like smaller. So we know that the one with the 3 carbon attachment is going to be our number 1. Then 2 carbons, 2, 1 carbon, 3. And then our 4th is going to be our hydrogen, right? So remember, we have to draw an arrow from 1 to 3. So 1, 2, 3, right? So this is a counterclockwise arrow, which is going to tell us that this is S, right? So we have an S conformation. So if we put this all in, so S dash 3T butyl, butyl, and then we put our parent chain 1 dash heptene, or we can use tert butyl hept dash 1 dash ene. All right. So there's both things that we can do. Both of them would give you the correct answer. Any questions on this one? Yeah. Yeah, so E and Z is going to be alkene stereochemistry, right? But it's only going to be used whenever we have 2 different groups on a carbon, right? So we have 2 carbons in an alkene, right? One carbon is connected to 2, the other carbon is connected to 2. If these 2 groups are the same on any carbon, then like on just the one. So this carbon has like 2 methyls, 2 hydrogens, 2 of the same group. Doesn't matter which, right? Then we're not going to have any E or Z. So in this one, we had this carbon on the left, our carbon number 1, it had 2 hydrogens connected to it, right? So in that case, the 2 hydrogens are the same. We're not going to have any E or Z. If one of these was a methyl and the other one was a hydrogen, then we have E and Z, right? But otherwise, we wouldn't. Does that make sense? Yeah. It's bonded to 3 methyl groups. Like this carbon right here, it has 3 bonds to other carbons. That's why it has 3 C's right beside it. Which Well, which carbon are you talking about? The car. Mhm. Right. So this carbon right here, right? We have one carbon that's bonded to three different carbons in this way. Do you see what I'm drawing? Right? So because it has three bonds to different carbons, this is going to be CCC, right? It has three carbon bonds. Versus the other ones, this carbon right here, it's bonded only two times to carbon with this double bond, and one time to this hydrogen. Does that make sense? The bottom one, this is bonded to two hydrogens, right? And then it has the bond to the next carbon, right? That's why it's CHH. Yeah. One more time. Does S go in parentheses? Yes. Or it could. It also doesn't have to. Sometimes they do want you to, but I don't think it needs to be. So yeah, that was a good catch. Thank you. Any other questions? Okay. We're gonna go on. So next section we have is facts. So it's saying in the box, draw the lower energy transition state for the process below. So whenever we have transition state, what we're gonna want to draw is like we're gonna want to draw the state in which both of them have a charge on it, right? So the lower energy just means that it's going to be easier for it to bond. So for example, we know that this hydrogen goes and bonds to this carbon because we see this, right? But this hydrogen is going to have a hard time breaking from the bromine just because an double bond wants it, right? Whereas if we look at the right side, this bromine is going to want to come to this positive charge. Like it's going to really want to come to this positive charge, right? So it's going to make it very easy for the bromine to come to the positive charge, which is going to cause that to be the lower energy state, energy transition state, right? So now to draw this, we can just do the R2 at R2C, bond to the hydrogen. And then we have CR2, and the whenever we're drawing transition states, we're not going to draw solid lines for the bonds forming. So this bond that's forming within between the carbon and the bromine is going to be shown as like a dash, right? We're going to show a dash and then the BR, right? And one last thing we need to do, we need to show partial charges. So this bromine is going to have a partial negative charge, and this carbon is going to have a partial positive charge, and that will be our lower energy transition state. Um, and yeah, if it's high energy, you're gonna use the slow step. Yep, exactly. You're gonna draw it from the not the rate determining step. So this is the fast step, as you can see, because this lower energy is gonna be the fast step, right? If it was asking for the higher energy transition state, you would draw it from the slow step. Yes. Intermediates. Oh, I see. Yeah, yeah. You would draw like an SN1. It wouldn't be in this way. Intermediate, you're gonna mostly just draw intermediates in the reaction section, right? And this one you wouldn't have to like draw because what the intermediate looks like is just gonna be like this middle part. Like this would be an intermediate, right? But the intermediate is given. Yeah. The partial negative is gonna be the one with the most electroneg is that's gonna be more electronegative. Yeah. Yeah, exactly. But either way, yeah, you'll get charges on the exam. Especially for these kinds of questions, you'll get charges. You don't have to worry about that. Yeah. What do you mean? So no, not for the R2C because that one isn't gaining any bonds or anything, and nothing's happening to it, right? So we're only going to show the ones that have that are going to be like interacting with each other. So in this case, it's the bromine and the carbon are with the CR2 with the plus charge on it, right? So that's why I do that. Yeah. If it said high energy, we would be. So I'll draw that for you as well. So blue. So if it says higher, this is going to be our slow step, right? So we're going to look at this one. So what we're going to have here is going to be something a little bit more complicated. So RC. So we're still going to draw the same thing, right? So we have CR2, and then this doesn't have any bonds to it. So we know that the H and Br bond, they're going to be breaking, right? So this H dash Br is going to be breaking. So we're going to show that by a dashed line. Then this hydrogen we know is going to this first carbon right here, right? So we're going to draw that forming with this, right? And we don't have any like positive delta charges on this one, right? So in this case, we just have our just like that. If you wanted to, you could put the bromine as delta negative and then the hydrogen delta positive, but or not the hydrogen, but the carbon delta positive, but I don't think it's necessary. Then we're also going to show, because this double bond is breaking, right? This double bond becomes a single bond. So this double bond is also going to have a dashed line. So if it was asking for the higher energy, this would be our higher energy thing. So it's essentially just putting dashes where the bonds are forming and breaking, right? Doesn't matter how you show them, just to know that the ones that are breaking and forming are going to be dashed. Yeah. So whenever we have dashes, we're showing that a bond is breaking or forming, right? So in this, we have an HBr, right? The HBr bond, between the hydrogen and the bromine, is breaking. So that's why we have to show that the HBr bond is breaking in that. That makes sense? Yeah. Yeah. It's not, I mean, you could, but I mean, it's not necessary because this is like the charge is so small that it's just like negligible. Yeah. Any other questions? All right. So have you guys gone over bicyclic compounds yet? Yeah. Okay, good. So number 2 is asking us to place the following alkanes in order of increasing stability, right? So 1 being least stable, 3 being most stable, right? So we know that an alkene, the more substituents it's gonna have, the more stable it's gonna be, right? So if we just decided to do that, we could have this one alkene which has 2 substituents. We could just call this 2 substituents. This alkene has 4 substituents, right? And this alkene has 3. So if we numbered it like this, we'd actually get it wrong, because whenever we have an alkene on a bicyclic compound, we need it to have 8 carbons or more if it's connected to a bridgehead. So what a bridgehead is this center thing right here, right? So in this case, we only have one alkene that's connected to the bridgehead, right? So this one is a bridgehead alkene, and what needs to happen is that this has to have a full chain of 8 carbons or more. So what that's gonna look like, if I was gonna draw it, let me if I was gonna draw a stable one, this is what it would look like. Just say I did that. I think that works. So if you look at this one, this is a bridgehead alkene, right? But this one has a 1, 2, 3, 4, 5, 6, 7, perfect, 8. So we need at least 8 carbons for it to be stable. And in this one, we have an 8 carbon chain, which makes this stable, right? But for this one, we have a 1, 2, 3, 4, 5, and 6 carbon chain, right? So this is unstable. So because of that, we're going to put this as the least stable compound, right? Number 1. And now we're going to look at which one has more substituents between the other ones. So the one with more substituents is more stable, right? So our next least stable is going to be the one with less substituents, so 2. And then the most stable is going to be the one with the most substituents, so 3. Are there any questions on that? Yes. Or okay, so whenever, yeah, sorry, I should have just specified which. Okay, so in this one, this alkene has 2 substituents, because if we're just looking at this, right? And so then this has 1 substituent and 2 substituents, right? So it's just these 2 carbons, right? That makes sense. And then on the right, we have substituent 1, substituent 2, and substituent 3. Right? 1, 2, and 3. Yep. No worries. Yeah. So what do you mean? One more. Yeah, so you need any chain in the alkene with 8 carbons or more. So that's why I drew this one. This would be like an 8 carbon chain, right? Like an 8 carbon cyclo. You understand what I'm saying? So in this one, we could have something like this. We could also have something like with more than 8. It just needs at least 8. So if we had this maybe, and then even like that, double bond right here. Then if we number this 1, 2, and 3, we can go 4, 5, 6, right? This is a 6 carbon chain, right? But we can also go up and down. So even if we did that, we still have to number 1, 2, 3, 4, 5, 6, 7, 8, not 8, 8, and 9. So this is a 9 carbon chain that I just drew, right? So it's like any chain that's gonna be all in a cycle. Yes. So so the bridge is actually a different cyclo. So if you wanted to look at it this way, think of the bridge as, I'm gonna erase this, but think of the bridge as like a different cyclo, right? So we have like a cyclopentane like this, right? And this way it's a cyclopentane, right? 1, 2, 3, 4, 5. So this one has 5 carbons if we look at it this way. And also if we started on the other side, we would have another pentane. 1, 2, 3, 4, and 5, right? So just like that, it's like coming like this together. Whereas we can also count it in this way, which is 1, 2, 3, 4, 5, and 6, right? So it doesn't matter how we count it. It's just that these are the only 3 ways that we can count it. Make sense? Yes. One more time. One more time. Sorry. Is the middle one what? Yes, exactly. So because it's connected to the bridge, it's because it's a bridgehead alkene, it needs at least 8 carbons for it to be stable. Since it doesn't have 8, it's unstable. Yeah, yeah. One more time. How many substituents is on the alkene? Okay, so every alkene, actually I'll try to show on this one, right? So we have the alkene, right? These alkenes have 2 carbons on each end, right? So one carbon can have 2 bonds to them since it's an alkene, right? So because this one has both of them, this one has 2 substituents, right? Does that, you see that? And right here we just have the hydrogen right here, and then this one substituent right here, right? So in that case we'd have our third substituent, right? So this is 3, right? Between 1, 2, and then our third, and then it has the hydrogen, right? Whereas if we looked at this one right here, this one has 1 hydrogen on either one of them. You see that? Right? And then we count the substituents that are connected to the carbon that the hydrogens are attached to, and we have 1 each. So this has 2 substituents. That makes sense? Yeah. Yeah. Not every time. So it depends on how big it is, right? How big the ring would be. Yeah. Then it would be stable. Otherwise, it'd be unstable. So if we had this exact like problem, but we had this bridgehead in the middle instead of this unstable one, this would actually be our most stable conformation. That makes sense? If you would, if there were more bridgehead carbons that were also, you would count them only if there was another like compound on this one. Ace, yeah, ace at least the sweet spot, yeah. But if there is more substituent, like if let's say there were two of the bridgehead ones, one of them had 3 substituents, one of them had 4, right? The one with 4 is going to be more stable, right? Yeah, no worries. Any other questions before we move on? Yes. Mm-hmm. Yes. Uh, okay. So we'll move on. So in the third question, it's asking us, place the following halides in order of increasing reactivity in E1 process. So whenever we have an E1 process, we know that E1 produces E1 is going to happen in tertiary, secondary, and primary, right? But it's going to be greater in tertiary, lower in secondary, and then even lower in primary, right? So if we look at each of these halides, this one is a primary halide. This one is a secondary halide, but I'll put an asterisk beside that. Secondary asterisk, right? And then this one is a tertiary halide because this carbon is bonded to 3 different carbons. This carbon bonded to 2. This carbon is bonded to 1, right? So in this case, you have a pretty clear idea of how to choose, right? But notice that on the second one we have a vinyl halide, right? So a vinyl is not going to be reactive, so non-reactive, right? So because we have this bromine on a vinyl position, it's going to be non-reactive to the E1 process. So this is going to be our least reactive one, even though it's secondary, right? And then moving on, so now we have it between tertiary and primary, right? So in an E1 process, the tertiary is going to be the most reactive compared to the E1 as shown right here, like this. So our tertiary is going to be our most reactive 3, and least reactive 1 would be our, or not 1, 2. Our least reactive would be that primary halide on the first one. Any questions on this? Yeah. So whenever we have this vinyl position, so a vinyl is whenever we have the alkene, and then one of the groups is a halide. So Br, iodine, like Br and iodine is pretty much all you'll see. Maybe chlorine, right? Br, iodine, chlorine, you'll have a vinyl halide, right? So in this case, that's going to be like just completely unreactive, right? Whereas if we had an allylic position, which is going to look like this, it's going to be 1 off. Then you'll have the Br, iodine, or chlorine. This is going to be very reactive, right? So it's really just like based off of one carbon, like which carbon is it on, right? So in this case, it's on the vinyl carbon, so it's not going to be reactive. But if it was maybe somewhere over here on an allylic carbon, it'd be more reactive. That makes sense? Any other questions? Yeah. E1 is like SN1 in the transition state, but it has a product like E2. Does that make sense? Like E2, so elimination, E1, E2 are both going to create double bonds, right? SN1, SN2, they're going to do, uh, what is it? Nucleophilic substitution, right? So they're going to substitute groups, right? Even though SN1 is a 2-step and SN2 is a 1-step, right? The same way E. Oh, yeah, yeah, it'd be the same. Yeah, it'd be the same way. Yeah, my fault. And then SN1 is going to be flipped, or SN2. Sorry, SN2 is flipped, right? Yeah. Any other questions? Yeah, yeah, same way. Yeah, it's in both. It's just completely unreactive. Any other questions? All right. All right. We can move on. So in this one, it's asking us to place the following alkanes in order of increasing bond dissociation energy, right? So in this one, bond dissociation energy is gonna increase with the lower the with less carbon bonding to the carbons bonded on. So for example, if I just did the same way, if I did 3, 2, 1 like this, it would be 3, 2, 1, but 1 has the greatest bond dissociation energy, right? So it'd just be flipped, right? So 1 is greatest, 2 is second, and 3 is the least bond dissociation energy. So in the same way, 1 is going to be our highest, right? So this is a primary carbon, right? This is bonded to 1 carbon right there. This is a secondary carbon, so secondary. And this is a tertiary carbon. This is bonded to 1, 2, and 3, right? So tertiary. So because tertiary has the lowest bond dissociation energy, we're going to put 1 right there. And then because primary has the highest, we're going to put 3 and then 2 in the middle, right? That makes sense for everybody? Any questions? Yeah. Yes, exactly. Yeah, it's about carbocation stability. So because carbocations, the primary carbocation is the least stable, is going to have the highest bond association energy, and vice versa. Of course. Any other questions? All right. Uh, technically, you're not going to have Fisher projections on your exam. So this section is entirely Fisher projections, but you're going to have diastereomers and enantiomers. So do you guys want to do this section regardless, even though Fisher isn't going to be on your exam? Yes. I think what's gonna happen is I think she's just gonna have like just 2 carbons like side by side and then just have wedges and dashes like this. You know what I mean? It'd be the same way like how this is formatted. It's just that Fisher projections like this wouldn't be on your exam at all, right? Cyclic? Oh, okay, so you might have cyclic structures as well. Hmm. Yeah, yeah. So I can go over this, but technically the Fisher projections won't be on your exam. So do you guys want me to do that, or do you guys want to skip it? Hmm? So okay, between them, I think maybe number 2 might be on your exam, just something like that. I'll redraw the second one. Because okay, so actually I'll just go through A. So A is a meso compound, right? You guys see that has like an internal line of symmetry between them, right? This OH goes to this OH, H and H, and then the CH2, CH2. Right? In the same way, this other side, right? OH, OH, HH, right? That causes it to be a meso compound. It's like divided by the middle. So this is actually an achiral molecule, right? So these are identical, right? So she might do that as well. She might give you a meso compound on them. So in that case, you'd have to know they're identical, right? So just look for internal planes of symmetry whenever you see one of those, right? So like in this, we saw the plane of symmetry going this way, going like this, like horizontally. And so we are able to make that distinction, right? The second one is probably going to be like the ones that I feel like you're gonna be the ones seen on your exam. So in these ones, because it only has 1 chiral center, you're not going to be able to get a diastereomer. Okay. So with a diastereomer, you need 2 or more chiral centers, right? So in this one, because we only have 1 chiral center, it's either enantiomer, structural, or identical. Okay. So if we look at this, um, so I guess this one is Fisher, but I'll just redraw it. Don't worry about this drawing right here. I'm gonna redraw it to the right. So this is going to be C wedge wedge OH and oh wait, I drew it wrong. CH2 CH3 H OH. Right. So it's the same. Fisher projection is kind of the same. Up and down just means dashes. Right and left means wedges. So that's not gonna be on your exam. I was just redrawing it so that you guys don't have to worry about like learning it. So in this one, now what we can do is we can look at whether there are or S or not, right? So in enantiomers, we're gonna have every chiral carbon flip, right? So if we had an enantiomer, right? Let's say we had an enantiomer of like something like this. It has two carbons. Man, can't even do that anymore. Wedge dash whatever, two groups R and R prime, and bonded to another wedge dash R R prime prime R prime prime, right? So these are two chiral carbons, right? So if we had if we had enantiomers and we had like let's say we had we have two of these molecules, right? So I promise this is worth it. Right? So if this left compound has two S's, like let's say these are both S, right? And these two compounds, they're both R's, like in terms of stereochemistry, right? So the S's flip to R's, right? That makes it an enantiomer 100% of the time, no full stop, right? If it has an S and an R, and then it becomes R and S, enantiomers, right? Same difference, right? As if they flip, both stereochemistries flip on both carbons, they're enantiomers, right? That goes for one carbon as well. So if one carbon is R and then the next molecule is S, this is going to be enantiomers, right? But if they're both S's, both R's, they're identical. If they're one carbon only, though. If they're one carbon and they're both S's or both R's, they're going to be identical. And then this one, let's say we have S and R, and then we have R and R, right? So one of them flipped. The S flipped to an R, but the R stayed the same. That's a diastereomer. Okay. So if there's like incomplete flippage, that's a diastereomer. Okay. Otherwise, if they're the same, S S, S to S, and R to R, that's identical. If they're polar opposites, S to R, R to S, that's going to be enantiomers. Any questions on like how to determine if they're enantiomers or diastereomers? Yeah. Yeah, probably. So cyclic are going to be the same way as this. You're going to have like two different cyclic chiral centers. The only difference with cyclic is that you have more groups, right? Not more groups, but you have like a bigger compound. Otherwise, it's still going to be the wedges and dashes R and S, right? All you're worried about is R and S, not over like all the other groups that are attached to it. Does that make sense? For the chiral centers of the cyclic compound. Yeah. Yeah, I could. If we had like, so let's say we had something like this, right? We have a wedge and a dash. This has CH3, CH2, CH3, right? And then we have another one. This is the wedge has CH2, CH3, and then this has CH3, and let's just put a methyl right here, right? So if we look at this, um, we have two different compounds, right? So on this top one, I'm gonna do that in green, right? We have we have two carbons, right? We have four carbons right here. So this carbon is CHH. It's bonded to one carbon, two hydrogens, HH. Then we have this carbon, which is bonded to three hydrogens. And then we have this carbon, which is CHH again. And then we have this carbon, which is bonded to one hydrogen and two carbons, so CCH, right? So CCH is going to take priority, so one. And then if we were to keep going, this carbon would have higher priority than this CHHH, right? This carbon would have HHH. This carbon would be CHH. So 2, and then 3, and then 4. If we were to draw from 1 to 3, right? This is clockwise, which makes it R. But our smallest group is on a wedge, so we're going to change that to an S. So this is an S compound, right? If we're going to do the same thing on this side, so 1, 2, 3, and 4 on the wedge, right? We're going to do that. and we drew this arrow, this is going to be R, and this is going to be the same, right? So in that case, because this top one is S and the bottom one is R, these are enantiomers, right? If they were both S, for example, then they'd be identical. And yeah, so that's the, yeah. Any other questions before I like get started on this one real quick? Yeah. So no. What I was talking about is between these two carbons, right? So let's I'll number them. So 1 and 2, right? We have 1 and 2 on, so 1 prime, 2 prime, and 1 and 2, and then 1 prime, 2 prime, right? So if 1 was R and 2 was R, right? Let's just keep them both R. And then 1 prime was S, 2 prime is S. Okay? That makes them enantiomers, right? Because it completely flips. Let's say 1 and 2 are R again, but this time 1 prime is an S and 2 prime is an R, right? So 1 prime flipped. 1 and 1 prime, they flipped. So it went from R to S, but the 2 prime was the same as the 2, right? That makes them distereomers, right? And then if they're R, 1 and 2 are R, and then 1 prime and 2 prime are both R's as well, that makes them identical. Okay, make sense? Yeah. All right. Yep. Any other questions? Okay. I'll go over this one example real quick, and then we can keep going. So in this one, we just have the same, we're doing the same thing, just finding out R and S. So for the one that's drawn, we have, we look at the biggest group first. So in this case, it's going to be our oxygen. So we have 3 carbons. We have 2 carbons, a hydrogen and an oxygen, right? So the hydrogen is going to be number 4 for sure, right? Our oxygen is going to be number 1. Now between the 2 carbons, this carbon is actually double bonded to this oxygen. This is an aldehyde, right? So in that case, this carbon has an oxygen bond, 2 oxygen bonds, and a hydrogen bond, right? So this is going to be bigger than this carbon on the left, which has 1 carbon bond and 2 hydrogens. So CH, and then this is OOH, right? So the oxygen is going to take priority. So this is 2 and this is 3. Remember, draw the arrow 1 to 3. So like this. So this is clockwise. So this is clockwise, so it's R. But then the 4th group, smallest group, is on a wedge. So this is going to go from R to S. Then to the right, if we can just number it the same way since it has the same groups. So 1, 2, 4, and 3, right? If we do this, this is going to be counterclockwise. So this goes from S, this is S, and then since the wedge is on hydrogen, this goes to R, right? So this compound is an R compound, right? Center that goes from S to R, right? So that's going to make this an enantiomer. Right? Does that make sense for everybody? Yes. So CHO indicates this. So we have C double bonded to an oxygen and an H. So this is the CHO group, right? So that's why I need to put OO, right? And yeah, in the back, the blue, sorry. One more time. It's not a structural isomer because structural isomers are gonna have the substituents flip. So structural isomers are gonna be on 2 carbons as well. But like let's say on carbon 1 we have a methyl, carbon 2 we have an ethyl, right? But then on the next one we have carbon 2 to have a methyl and an ethyl, right? That would make it structural, right? Yeah. If it was R, yeah. If it was R and R, it'd be identical. If it was S and S, it'd be identical. But yeah, since they're R and S, these are enantiomers. Any other questions? No? Okay. We're gonna move on. I won't do number C. So number 6, she went over this in your lecture. So this is like kind of a lecture question. It's asking if the compound below is chiral or achiral. So if this was achiral, what she's expecting you to find out is if this is a meso compound or not, right? So if you look at this just straight on, you see these iodines and these bromines, they're like completely, they can like literally flip onto each other, right? Like on the paper. However, these are actually going to be chiral molecules, and I'll explain why. So whenever they're achiral, we know that achirals are going to be meso compounds like that, right? So because we know, so this isn't a meso compound, and the reason it's not is because at the top, these iodines, think of these as really big groups, right? If they're so big that they can't really give space for each other, right? So like let's say this iodine is this big, there's not going to be enough space with that overlap, right? So what's going to happen is because this is just a single bond, we have one side, one benzene ring that looks like this, right? Just like flat on the paper. And then we have another benzene ring that's instead of being flat on the paper, is going to be like coming out of the paper, right? It's going to be like laying on its back, like if we looked at it like this, right? So there's one benzene ring like this and another like this, right? They're both bonded. So this one is going to be a chiral molecule and not achiral. Does that make sense? So like the groups, they can't coexist like this, right? So they have to coexist like this, right? That makes it chiral. Yeah. Yeah, they can't be achiral. Yeah. That makes sense. It's just a conceptual question that you covered in lecture. Yeah. On what? So achiral means that it's not gonna have, so something that's achiral is like not gonna have any chiral centers, or it's gonna be a meso compound, right? So something with no chiral centers might be a carbon that has two of the same groups. So H, methyl, and ethyl, right? So even though it has four groups on it, there are two of them are the same, so it's going to be achiral, right? In the same case, an achiral molecule is going to be something that can also be flipped onto each other. So this A, like this one A, this is able to be flipped onto each other, right? Like just like this, because there's no stereochemistry on it, right? So it's able to flip. That makes it a meso compound, achiral, and identical, right? Essentially, this is trying to get you to see if you can understand if it's a meso compound or not. So because we know it's not a meso compound, because there's too much steric, we know it's gonna be not achiral. So it's gonna be chiral, right? That makes sense? Yeah, the two of the groups are the same, but this is more talking about the whole molecule as a whole, not like as a carbon, right? It's not asking if the carbon is chiral, it's asking if the molecule is chiral, right? So if the molecule, this goes back to like what is it, optics? What do they call them? It's like the reflectivity or whatever. No. There's like optical, yeah, optically active or optically inactive, right? So if it'd be inactive, it'd be achiral, and actives are going to be chiral. Flipped? Yeah, racemic mixture. That, yeah, optically active is the one per sample. Oh, really? Okay, yeah. So optically active is going to be like an achiral molecule. So an achiral molecule is going to be optically active, and optically inactive is going to be something that's not going to be achiral. It's going to be something that's chiral. Flip again. Flipped again. Oh, 10%. Oh, that's not good. So if it doesn't have chirality, okay, it's inactive. If it's achiral, right? Okay, so in this, it's just a different concept that you just have to know, I guess. In this case, it's just steric hindrance, but between them, yeah. It's essentially just saying that this molecule has to go one way, like if it's flat, the other way has to be like laying down because the groups can't coexist like this. You understand what I'm saying? Yeah, no worries. Any other questions? Yeah. So the bromines are also big groups. Yeah, they can't coexist. I low key. Okay, I'm gonna try to get through this exam before my iPad dies. So I'm gonna try to get no questions in, but I'll get questions at the end. Okay? Yeah, sorry about that. I just don't want it to die on the while going through it. Okay. So the next one, in the box provided, place the letter of the reaction with the faster rate. So if the rate is the same, right, same in the box. So in this one, we have an SN2 process. We know this because this is a primary halide, and this is also a primary halide. But so in whenever we have primary, we're gonna mostly lean towards SN2, right? So in an SN2 process, we want an aprotic solvent. So what an aprotic solvent means is that it's a solvent without any hydrogens on it, right? So this H2O has hydrogens on it, but this acetone actually looks like this. So O, like this. So it doesn't have any hydrogens on it, right? So this is going to be, it doesn't have any hydrogen bonding in it. Sorry, this one has hydrogen bonding, so it's protic. But acetone is aprotic, right? So because of that, this acetone is going to be our reaction with the faster rate. So we're gonna write B in the box. All right. Reactions. So sorry, I'm trying to. I don't want this iPad to die. So NaCN. This is going to be another SN2 reaction. So SN2 increases in rates whenever we have primary, then secondary, and it doesn't occur on tertiary. So tertiary, it's not going to occur, right? So we'll look at primary and secondary positions, right? So this bromine, we have one on a vinyl position. We already established that vinyl isn't going to react, so we're not going to worry about this bromine changing, right? This bromine is on a secondary position. So secondary, this bromine will react, no worries. This one is on a tertiary position, so this bromine will not react, okay? So we only have one CN that's going to be reacting. In this case, SN2 is 100% inversion, right? Inversion. So whenever you have an SN2, this Na plus Cn minus, so, well, it's on the nitrogen, I guess. So the nitrogen is minus, right? This is going to come and, no, the nitrogen is not minus. I lied. The C is minus. So Na plus C minus. This C is going to come and attack the bromine from the back, like this. And it's going to cause the stereochemistry to flip, right? So this is going to move over here. The bromine is going to come off all of this, right? And so what we're going to have as a product is going to be this with a Br right here. Then I'll draw the rest of the compound out. CH3. We're going to keep this Br on here. And now we have a different group on this wedge right here. So we have this wedge with a Cn now. And we have this dash on for the hydrogen. So now the hydrogen has a dash on it, right? So we have the cyanide and the hydrogen. And that's going to be our 100% inversion reaction with SN2. So you'll notice that the halide was substituted with with our nucleophile. Okay, so moving through, this is Fisher. I'll still go over it because you guys do have to know about anti-coplanar. I can't answer questions, but I'll do it after the exam though. Sorry about that. So I'll do whenever we have anti-coplanar. So whenever we have any elimination reaction, we want anti-coplanar, halide, and hydrogen. So in this case, we want this bromine to be anti and coplanar to another hydrogen. So we want this to be a hydrogen here, right? So what we're gonna redraw this. I'm gonna redraw it outside of a Fisher projection, so you guys don't have to worry about that. So this is going to I'll redraw it first, just like as a regular compound. So wedge Br hydrogen and benzene and dash benzene and our CH3. So this is our the same compound that's like this, that's shown like right here. I'll draw like our flip compound. So what we want is for this Br to have something like this to the like this, right? This is the anti-coplanar, right? So what we're gonna do, we're gonna move this hydrogen over, we're gonna move this methyl over, and we're gonna move this, right? So we're gonna make the three-way flip. So now we have on this carbon and this carbon the line H Br H. So now that we have the anti-coplanar, we can do our groups. So this O minus is gonna come and attack this hydrogen. So this is an E2 reaction, right? So E2 is gonna be one step. So this is gonna attack this E1, sorry. Oh no. So this is an E1 reaction, sorry about that. So what's gonna happen first is this CH3OH is gonna protonate this Br, which is gonna cause it to leave, right? So we're going to have a transition state, not transition state, but an intermediate product. So this product, I'm pretty sure you guys do have to draw if you want full credit. So you don't have to draw what I just drew, but you do have to draw this. Actually you might, but I would draw it just to be safe anyway. But you do have to draw the intermediate state for full credit. So CH3, this becomes the same thing. H. And now this carbon has a plus charge on it, right? Because that bromine left. And then we have our benzene and our hydrogen, right? So because that left, now this O minus wants to, this small strong base wants to go and attack this this hydrogen. This hydrogen is going to go with that O minus Na plus, and it's going to stabilize this positive charge, right? So at the end of the day, we're going to have an alkene, right? But now we're going to use the wedges and dashes to inform how the alkene is oriented, right? So notice on the wedges, we have, well, on the wedge, we have on the left side, we have the benzene and the hydrogen, whereas on the right side, or on the dashes, we have the methyl and the other benzene, right? So we're going to have one benzene on each side. Doesn't matter how we put it. So we'll put, because one benzene is on a dash, one benzene is on a wedge, right? So like that. And then we're going to have the hydrogen connected to one and the methyl connected to the other. So we're looking at this way. This CH3 and that benzene ring, this is on a wedge, or this is on a dash, this is on a dash. And then this bottom one is I'll do this in red. So this one and this hydrogen, these are on a wedge, and this is on a wedge, right? So those are going to be across from each other. So everything that's on dash is across from each other. Everything on wedge is going to be across from each other. So this is going to be our product, right? Going on, NBS and light. So this creates an my bad. So This creates an allylic bromine. So an allylic position is going to be something that has a double bond, the single, and then on that next carbon has the halide. So halide, which is going to be I, Br, or Cl, right? So it has one of those, right? So one thing to note, we have two boxes here, right? So that means there's going to be two different products. So NBS actually doesn't only just put a bromine on, right? It's actually a radical bromination. So it creates a radical on an allylic position and then it puts a bromine on. So what we're gonna have here is we're gonna have our bromine radical created. So there are three places that are allylic to this double bond, right? We have one place right here, one place right here, and one place right here, right? But the radical has to take the place of a hydrogen. So in both of these, no hydrogens on either of these carbons, right? So that neither of those can be our radical position. So we're gonna look at the top one only. So our top one is gonna be the only one that's gonna be having a radical. So 6, 5, 1, 2, 1, 2, double bond. Like that, right? So in this, notice that we have the double bond right beside the allylic position. That means that we also have resonance here. So we can do our half arrows. Remember, we use half arrows with um we have half arrows whenever we do resonance with radicals, right? So we do our half arrows like this, and we're showing that the double bond is created up there, and the radical moves to the tip of that cyclopentane. So we have this like this, and then cyclopentane, boom, boom, right? And now that we've done that, all we have to do is add bromine to positions. So make sure that you show that these are resonance, that these are just resonance contributors of each other, right? And now all you have to do where those radicals are, you put your bromines. So in this one, there's not like a major or minor product, so you just go ahead and do it. So bromine right here. And then we have our this. Notice how both bromines are like allylic, or both bromines are on an allylic position. So these are both valid answers. So going on, this one we have OTOS. This OTOS is a good leaving group, but more importantly, we have this reaction right here, right? So this is actually a this reaction is actually E2, right? But that's because this is a bulky base. Bulky base. So if you were to draw this out, this nitrogen just has 3 ethyl groups coming off of it, right? CH2, CH3, CH2, CH3, CH2, CH3. So this is our bulky base, right? So for that, whenever we have E2 with a bulky base, oh, also sorry, this box is supposed to have major and minor. So major and minor. So you have one box on the exam that'll tell you which ones ask you which one's the major contributor, which one's the minor contributor, or the major product and minor product, right? So in a bulky base, the major product is going to be the least subbed alkene. This is because the bulky base can't get to more substituted hydrogen, which causes it to is because it can't get to there, like as it's not as accessible, it's gonna be less product is gonna be of that more subbed alkene. I guess I'll explain to you in this example. So this bulky base, um, it attacks a hydrogen, right? So in this case, it has to attack a hydrogen on a carbon that's adjacent to this OTOS group, right? So it can attack a hydrogen here, it can attack a hydrogen here, and attack a hydrogen here, right? So there's only one hydrogen here, right? And it's let's look at this. It's protected by two ethyl groups, right? So there's a lot of steric hindrance if this bulky base was to come and take this hydrogen, right? So this hydrogen probably won't happen. So we can just cross off this double bond from forming, right? That's not going to form. Now this hydrogen, this has just it has two hydrogens, and it has just one methyl group coming off, which makes it a pretty good like choice for this bulky base to come and yoink a hydrogen. But this other carbon, this methyl group that we have, is also has no groups that are defending it, right? It just has the three hydrogens on it. So because of that, because this is our smallest thing, it's easiest for this bulky base to come and take one of these hydrogens. So that's going to be our major product, right? So our major product is going to be this OTOS group leaving, right? A hydrogen of this is going to come and create this double bond, while this N comes and takes this hydrogen, right? So our major group is going to look like this. And then this is our CH3 group, and it becomes an alkene, right? Versus our minor is going to be whenever this double bond is created. This OTOS leaves the same way. I'll do this in a different color, actually. So we have two hydrogens, right? So this N comes and takes the hydrogen. This goes and creates this double bond instead. And then this OTOS group leaves, right? So what that's going to look like is going to look like this. The methyl group right there. Going on. BrCH3. So whenever we have CH3OH in heat, this is going to indicate we have an SN1 reaction, right? So SN1/E1. So we know that SN1 is always going to have pretty much two products, right? SN1 is going to have the 50% inversion and 50% retention. That means that the halide position is going to be substituted, but 50% of the time it's going to be going from wedge to dash, and 50% of the times it's going to stay from wedge to wedge or dash to dash, right? So in this case, we have CH3OH in an SN1 reaction or an E1 reaction. We always have a not transition state, but an I literally just said it. It was it does anyone remember? It was the started with an I. No, not that. No, sorry. Okay, anyway. Sorry. No, not that. My bad, my bad. So we have the middle product, which is like not our transition state, but it's called something else. Intermediate, yeah, exactly. Sorry. So we have our intermediate. Our intermediate is going to be whenever this bromine leaves, right? So in SN1 E1, it's a two-step. So the first step is that the halide leaves. So our leaving group leaves. So in this one, we have our CH3 like this on the wedge, and then we have our plus charge, right? CH3. And now we have CH3OH in heat, right? What this is going to create is going to create an SN1 product. It's going to create two SN1 products, right? This is going to attack, and it's either going to have the inversion or the retention, right? So we have two products. So we already have two of them, right? We add the wedges and dashes. So on the retention is going to have our CH3, OCH3, right? And then not this. OCH3 is going to be on the dash. So OCH3 on the dash, and then the CH3 on the wedge. And then on our inversion, we have same thing. Wow, that was bad. With the OCH3 on the wedge and the CH3 on the dash, right? But now it's asking us one more. And so this is going to be our E1 product, right? So on our E1 product, we want our most substituted, most subbed alkene, right? So within our most subbed alkene, we can have an alkene that goes like this, which is going to be 3 subs, right? We can have an alkene like this, which is going to be 1, 2, 3 subs again. So 3 subs, and then we have this alkene, which is 2 subs, right? So we're going to choose one of the 3 subs to create, right? So in this case, it'd be the same thing. We have our intermediate. It's the same intermediate between all 3 of them. So our third one is going to be, we're just going to draw one of these alkenes. So it doesn't matter which one you draw as long as you draw one of them. So both of them are going to give you full credit for SN1 at least. So I'll just draw this one. You can draw the other one if you want to, but this one is the one I chose to draw. Going on, NaNH2. This is a small, strong base. So what this is going to create is this is going to create SN. This is going to not. It's going to be SN1E1, but this one in particular is going to be E1. Right. This is an E1 reaction. So in this one we have a cyclohexane with 5 groups that are all on wedges. Right. So whenever we have an elimination reaction, we want something that's transdiaxial to a halide. So we want a hydrogen that's going to be transdiaxial. What that means is that between two things on the periodic on the chair structure, we want one group, the halide, to be on an axial position, so CLIBR whatever, and we want a hydrogen on another axial position adjacent to it, right? So we want that hydrogen. If the hydrogen is on a equatorial position, so if the hydrogen is here, it's not going to react. And if the halide is here on an equatorial position, the CLI or BR, it's also not going to react. Okay, so it doesn't matter if it's on equatorial, it's not going to react versus an axial position. So we want it to be on an axial position, right? So in this one, we have 2 of them. So we have to determine which one is going to be reacting, right? So the best way to do that, we're going to draw a chair conformation. Remember, when drawing a chair conformation, we're always going to start with the biggest group, right? So this this T-butyl group, chickenfoot, is going to be our biggest group. So this is going to be going on an equatorial position all the time, right? So I'll just choose an equatorial position. I'll choose this one, CCH3, 3, right? So, and now we can just keep going. So if we number this 1, 2, 3, 4, 5, and 6, 1, 2, 3, 4, 5, and 6. So on carbon 2, we have a methyl facing up. So this is our methyl facing up. Then carbon 3, we have our chlorine facing up, which is going to be equatorial facing up, Cl. And then carbon 4, we have our chlorine facing up, which is going to be Cl. This is going to be an axial position. Carbon 5, we have a methyl facing up. This is going to be equatorial, CH3. So between these, our chlorine on carbon 4 is going to be our axial halide, right? So that's going to be the one reacting. So between them, we have 2 hydrogens that we can choose, right? So we have this hydrogen down here and this hydrogen right here between 4 and 5 and 3 and 4, right? Oh my gosh. Okay, so we have 4 and 5 and 3 and 4, right? So we have 2 double bonds that can be made. So one of them is between 4 and 5, one of them is between 3 and 4. Both of them are valid, but the one between 4 and 5 is going to yield a double bond that has how many substituents? If we counted them, we would have 1 substituent, like this, 1 substituent and 2 substituents. Whereas if we drew one from between right here, we would just have the this substituent right here and this one right here. So we'd have 2. Sorry, we have 3 because this one is also a substituent. So between 4 and 5, we have 3 substituents. And between 4 and 3, we have 2 subs, right? So we're going to take the 3 subs over the 2 subs. So this is going to be between 4 and 5. So we'll just draw this right here, and then we'll draw our final product. So remember in E1, this chlorine leaves. So this chlorine leaves, we'll draw our chair structure once again. Plus charge right here. Cl methyl chicken foot, and then CH3, right? And so then this hydrogen is going to be attacked by this NH2 and A. So this is a minus charge plus. This is going to attack this hydrogen. This hydrogen is going to go and create a double bond to stabilize that positive charge. So our final product is going to be this cyclo with the same, so our chicken foot over here. Then we have our, on the next carbon, we have CH3. Next carbon, we have our Cl. And then between, so if we count 1, 2, 3, 4, 5, and 6. So between 4 and 5, we have our double bond right here. So I'll draw that right here. 4 and 5, we have our double bond. And on 5, we have our methyl group. And that's going to be our final product. Next one, mechanism. Which better not have 5. Okay. So mechanism, this is an SN1 reaction. So remember, whenever we have heat, it's usually going to be SN1 or E1. So in this case, because we're not creating any other double bonds, it's just going to be SN1, right? So in a mechanism question, we have to draw every single arrow, every single thing that happens in the reaction, right? So the first thing that happens in an SN1 is that the bromine leaves, right? So we can just draw this bromine leaving. So the bromine leaves, and now we draw the new product, right? Dash CH, CH, double bond CH2, positive charge right here, right? And so now the next step for the SN1 reaction, well, not the next step, but the next step is in a mechanism, we want to create these compounds right here. So let's call this A, let's call this B. I should have done this earlier. So on compound A, we see that we have on the first 2 carbons, we have a double bond, right? And then on the last carbon, we have our OCH3 group. So on this, we have the double bond and the potential group flipped, right? The group can come onto this positive charge, right? But what we can do here is do resonance, right? So we're going to draw this arrow to show that this double bond goes and stabilizes this positive charge, right? And it's a resonance structure or a resonance contributor for this product right here. So we have this CH double bond CH dash CH2. And notice how the plus charge is now on the very end, right? So it's exactly how we want this to be. It's just that now we have to add this OCH3 group, so our ether, right? So what we want to do here is write our CH3OH. And we're going to show this lone pair going and attacking that positive charge, right? And so what it's going to do, it's going to form a compound. So we'll draw an arrow right here. So it's going to form this compound right here, like this. CH double bond CH dash CH2 dash O dash CH3. But this oxygen still has a hydrogen attached to it, right? So this oxygen now has a plus charge. So our last step in mechanism is to deprotonate. So deprotonate. We can do this either by O minus CH3, or we can use the Br minus. I like to use the Br. So Br minus comes and takes this hydrogen, which then stabilizes this oxygen. And then now all we have to do is draw the final product. So this is our final product, and we are done with that first A, right? And now for B. So on B, we have a 6-carbon ring. So this is going to be a ring opening, right? So I'll do number B in green. So what I'm going to do, I'm going to redraw this first compound. So this is our first step for all SN1 reactions, right? So it doesn't matter like how we do, I'm just gonna redraw this. Don't have to redraw it, but it's nice too sometimes. CH double dash CH2. So in this, notice we have our positive charge and that we have a ring opening, right? So what this does is that we're gonna have what I like to do is I like to start numbering from where the where the charge is, right? So 1, 2, 3, 4, 5, and 6. So if we have a 6 carbons and all of them are accounted for, what we can have is this carbon 6 creating a bond with this carbon 1 instead of it having a bond with the carbon 2. So this carbon 2 bond is broken, right? So the carbon 2 bond is broken, and then the carbon 6 creates a bond with carbon 1. That creates our cyclohexene right here, as shown in the second one, right? So we have our ring opening. So ring opening. And then we have, well, yeah, I'll draw it the way that the question is showing. Like this, we have our cyclohexane, CH double bond CH2. Remember this CH that had the plus charge on it is now inside of this ring. This is this CH right here. So this CH and this CH are the same. And now we can start just counting. If we count this as carbon 1, 2, 3, 4. So 3 and 4 is where our double bond was. That's the exact same spot. 3, 4, 5, 6. And now we know that this carbon 2 lost a bond, right? This carbon 2 once had 1 bond, 2 bond, and 3 bonds. But now it's lost this third bond, right? So this carbon 2 has a positive charge on it now. So we're not going to draw it on this one. We'll draw it over here. So 2 now has a positive charge. Plus. Right? And if we look at the product, exactly where that positive charge is, we have our OCH3. So we're going to do the same thing. CH3OH is going to attach that positive charge. Lone pair, tags, beautiful. Right? It creates the same product. So mechanism is a lot of repetition, you know. So we have this OHCH3. This O is still going to have our positive charge on it, so we're still going to have to deprotonate it. So the way we can deprotonate it, we can use Br minus or OCH3. This time I'll use OCH3. So it's going to take that H, and that H is going to stabilize that oxygen. And now we have our final product, which is this cyclo double bond and this OCH3, right? So I'll do the last question, the synthesis, and then I will end the meeting and take questions. So the first thing that you want to do from synthesis is read the instruction. It's asking you to synthesize the molecule below from cyclohexane, alkanes, or four carbons or less, right? So if it has more than 4 carbons, we're gonna have to break it down, essentially. Just have so yeah. So now, whenever we wanna break this apart essentially. So we're gonna break it apart at the oxygen bond. So this oxygen is bonded to this cyclohexene structure, right? So we're gonna break that bond. And the way we're gonna do that is through heat. So that bond is formed through heat. So this bond is formed through, well, you can write heat or you can just write the delta, which shows heat, that indicates heat. So this is gonna give us our cyclohexene, right? And at this point, we can't just have like a bond forming, right? We need a halide to take because we have a SN1, right? SN1 reaction, nucleophilic substitution. This is a nucleophile. This O And this entire group of the oxygen is a nucleophile. So this is going to be SN1. So that means this is going to have a Br on this position instead of that oxygen. And so this combined with whatever, we're going to have this, and then we're going to have this oxygen with the hydrogen on it, right? Because this oxygen with the hydrogen plus that bromine, this is the key for our SN1 reaction, right? We have our weak nucleophile plus heat, right? So weak Nu and then plus that heat, that's our SN1 reaction. This is our key for that, right? And then to get our OH onto this, I'll do this side first. To get our OH onto this is going to be through H2O and heat. O/heat. This is another SN1 reaction, right? And we're just gonna have our bromine being here instead of this OH. So this is now a bromine, right? And the way to put a bromine on this position, we have to look back. To put a bromine on this position, we have to get sorry. Remember, this is an allylic position, right? So the alkene, and then we skip a carbon, go to that one, and then that one has a bromine. So the way to put a bromine on that is through NBS, right? So in this case, we have NBS, and what that does, if we show it like this, it forms this compound into the compound shown above, right? This Y becomes that compound shown above. And now to get rid of that double bond, what we can do is an E2 reaction. So T-butyl O minus Na plus. Also the NCH2 CH2CH3 3 would also be good. If you wanted to do this instead, this would also be fine to use either of these, and that would cause an SN2 reaction. So now we have our bromine like this. And remember, we have to put a bromine here because whenever we do our starting, we're going to use Br2 in light. So this is always going to put the bromine on the most substituted position, right? So the most substituted position in this case would be the center, which would be a tertiary carbon. So this puts the bromine on the tertiary carbon. And so to begin, we have our our 4 carbon chain, 1, 2, 3, 4 carbon chain in excess, because Br2 in light is a low yield, it's not used for monobromination, it's used for multiple bromination whenever we have an alkane, right? In the same way, this time we have the bromine on the allylic position already, right? So we're going to start using NBS, and we're going to get rid of that bromine. And it's essentially going to take the same shape as before. We're going to use SN2 to get rid of this double bond. So SN2, well, not SN2 here, but this is an SN2 reaction. So the T-butoxide, O minus Na plus, like this. And that's going to cause this cyclo to have a bromine wherever it is. And then that is going to be added Br2/light. And we have our cyclohexane, not that. Okay, so we have our cyclohexane in XS. So remember, whenever we do our first compound with Br2 and light, we always have to have our alkane in excess, right? Because if we don't put excess, what's going to happen with Br2 and light is that it's going to go from, like, if there's only one, like, if we didn't put excess, right? And let's say we only had like one molecule of cyclohexane, this Br2 and light is going to add bromines all over. Br, right? So we don't want that. What we want is just monobromination, and that's why we have to write the excess. All right, does that make sense? I can take questions now, but I'm gonna end the Teams meeting first, and then you guys can come up. Yeah, did I say that? Did I say SN2? Oh, my fault. Yeah, this is an E2 reaction. I don't know why I said SN2. Sorry about that. I wrote S again. Dude, I had no idea my iPad was this low. Otherwise, I would take so many more questions. I'm so sorry.